Test-driven development is the norm in software development best practices these days. As such, this approach is strongly recommended when developing smart connector extensions. Choosing which unit testing framework to use, however, is less clear. Whether you choose Visual Studio testing, NUnit, XUnit, or another framework is largely a matter of developer preference, and a discussion topic that is beyond the scope of this video series. For our purposes, we will use the NUnit 3 testing framework. As an incentive to using NUnit, Buildings Labs provides a NuGet package to facilitate test writing with NUnit. Before we can begin writing tests, we need to complete some housekeeping steps. You will need to install what is known as a test runner. If you have the ReSharper extension in your Visual Studio, you can skip this video. As you know, you can get it from the newly added ReSharper tab. And open up their own custom unit testing window. But for the purposes of this training, we want to use NUnit 3. So you would go up to Tools, Extensions and Updates. You want to go to Online over here on the left, Visual Studio Marketplace. Search for NUnit. And this is exactly the version you would want to get. As you can see, we already have it, but if you don't have it, then you'll see this download button. Click Download and install it, and when prompted to, restart Visual Studio to get your NUnit 3 test adapter in here. After that, you should install Smart Connector. This is explained in the Smart Connector installation and configuration guide. Once you have that and Smart Connector installed, we can actually create our unit test project. So here in the Solution Explorer, you're going to add a new project. Go to Installed Visual C#, and you want to choose Class Library .NET Framework once more, and the appropriate .NET Framework you want to target. And we need a name. And here you go. Actually, we should have the naming convention be consistent. And now our test project is going to need references to our extension assembly. So we go here, add reference. We got there by right-clicking and then selecting add reference. Come over to the left on Projects, Solution. This is the reference that we want to add. We also need a reference to Smart Connector. So right-click, Add Reference. we're going to have to browse to find Smart Connector. Now what you have to do is that you have to find the Smart Connector installation folder. And what we're looking for here is mongoose.service.exe. Right here. Now, when extension code runs in a production environment, it runs in the process space of Smart Connector. And as such, connection strings and encryption keys are read from the mongoose.service.exe.config file. However, in our unit test environment, extension code is invoked from unit tests running in the process space of our test assembly. As a result, we need to copy the pertinent information to our test assembly configuration file. So we right-click here, add new item. We go to General, Application Configuration File. The default name is fine, and we'll just simply click Add. Now we need to navigate to the Smart Connector installation folder. And locate mongoose.service.exe.config. Edit it in whatever text editor you use, and locate the connection strings element right here. Copy the entire contents between the opening XML tag and the closing one. Now go back to the app config you just added and paste that element. Actually, more specifically, we should get all of this. Now repeat all of these steps for the encryption key setting, which is to include the app settings element. Right here. One final step remains. Building Labs supplies a NuGet package specifically intended for test purposes. So again, we're going to right-click References, Manage NuGet Packages, Smart Connector. Include pre-releases must not be checked. You want to install mongoose.test. Now it's time to add our first test fixture class. We can just simply repurpose class 1. We will call it setup processor fixture. It should be a subclass of Smart Connector text fixture base and iProcessor test fixture. Type of setup processor. You'll notice Visual Studio is complaining with red syntax about the iProcessor test fixture interface. So what is the problem here? What about here? We are using mongoose.test and mongoose.test.processors. Looks like we only need to implement the abstract class. Well, this is interesting. It was supposed to stub out 3 different tests, but it hasn't done that. While Visual Studio is good at stubbing out known interfaces, it doesn't supply everything we need. While convention dictates unit test methods names should end in test in order to make these methods callable from the NUnit test runner, we must add test attributes to them. So I'm going to implement those methods all very quick and then add the test attribute. This part will be sped up. NUnit provides attributes which can be used to decorate methods, so that they run before and after the actual tests run. These are useful for performing setup type operations required for any and all tests included in the fixture. Much of what we needed to run a Smart Connector fixture is already handled for you in the Smart Connector test fixture base class. Of course, there is one step that is typically needed that can't be performed for you in the base class: initialization of the inversion of control container. Luckily, this code is available as a static method from the service reference itself. We can easily provide the required code for fixture one-time setup base. Luckily, this is very easy to do. Real quick, right here at the top of the class, we have to add the test fixture attribute. And now we can come down to one-time setup base. You want to call Smart Connector Runtime dot initioc. Okay, there's one more thing we need to do. Add a reference to system.serviceProcess. And there you go. Using the iProcessor test fixture interface as a basis for writing unit tests for your processor code focuses on testing three major aspects: processor validation, execution, and canceling a running processor. In all of these scenarios, an instantiated processor instance with valid properties is required. Create testable processor provides that instance. To be clear, this method is not a test. Rather, it is a support method which the other test methods will incorporate. While an extension method of iProcessorTestFixture is available to do most of the work here, in most cases, more information is needed than the test code needs to supply. So we can set this up right here. Here we go. Just call this.createProcessorInstance with default values. And again, if you want to find the address, you just simply go to the processor base right here, whatever you set it to. Or did we not set it here? No, we didn't. Oops. And finally, just return processor. This line right here invokes an extension method which returns an instance of setup processor with the default values that we set. And then we add the additional information right here that our test will need. The validate test is meant to work interactively with create testable processor. First, we will call create testable processor and then run the extension method to confirm no issues are initially present. Following that, it is up to the test author to manually produce validation issues and confirm that they are detected. The depth and breadth of this validation confirmation is really up to the test writer, and what is shown here is merely a guideline. You want to call this .validate processor, which performs deep syntactic and semantic validation on the supplied processor and is going to return all the issues found. And now you want to do an assert call. The assert class contains a collection of static methods that implement the most common assertions used in NUnit testing. So we want to assert.r equal. Now, this verifies the two doubles are equal considering a delta. If the expected value is infinity, then the delta value is ignored. If they are not equal, then an assertion exception is thrown. Now, how does that play into what we're doing here? Well, we'll put in a 0 and then issues dot count. We simply just want to call NUnit's assert method to make sure that there are 0 issues. And you can simply add more validation as needed. The execute test down here mimics what the Smart Connector runtime does when a processor configuration is commanded to run. In this case, an easy extension method is available. We'll see this very soon. very simply, just call this .run execute test. The cancel test is similar to execute test, except that shortly being invoked, an abort is simulated to ensure that your processor exits in a timely fashion. As with execute test, an extension method is also available for you to call to perform. You've guessed it, this .run cancel test. Debugging your tests is as easy as opening the Test Explorer in Visual Studio. You can use this to browse all detected unit tests. It will be useful later when we have tests with the same name to group them by fixture. This is accomplished by clicking the Group By icon located in the top left corner of the Test Explorer and choosing Class. As you can see here, that's already defaulted. It is grouped by setup processor fixture, and you can see all these different tests. Once displayed, you can either run or debug a single test, all tests in your fixture, or all tests in your project. Debugging will allow you to set breakpoints in your code and step through to find any issues in either of your test code or processor code. So if you wanted to do this, let's say the execute test. If you wanted to simply run it, right-click, Run Selected Tests. But if you want to debug something, so let's say that in ensure value item, we want to know if var vi is not null. Set a breakpoint here. And for the execute test for the setup processor, right-click and debug selected tests. So then as the processor is running, it'll eventually hit this breakpoint. Pretty nifty, huh? And now, adding a test fixture for the update processor should be fairly straightforward at this point. I will let you do this on your own, but if you're unsure of exactly where to start, you can look at an example class file that's included in the supplementary materials. Our next step is to continue on to deployment of our extension.